Okay, let me start the recording. All right, so the goal is to start the new chapter of oscillations and waves. It is also termed as vibrational motion, right? And so coming from AAS, you are all probably familiar with waves. What are waves? What is an oscillatory motion? If anyone is not familiar with the idea of waves and oscillatory motion, they can let me know, or also let me know if you are familiar with the idea of waves and oscillations, as in what these terms mean, basically. We know that we can say, for example, an oscillation, you can say for an oscillation that it is really a motion which repeats itself. So it's something like going back and forth. For example, if I hang from a ceiling, suppose this is the ceiling, and I hang a string, and on the string I attach any mass, suppose it's a ball, and so the perpendicular, if I drop a perpendicular from the ceiling, that looks something like this, and I raise this to some displacement, which is known as the angular displacement. We must all be familiar with these terms from circular motion as well, right? We discussed all of these things in circular motion. Now, if you displace this pendulum, it's called a pendulum, by some angle theta, you'll notice that as soon as you release this thing, it will start oscillating like this. So what it will actually start moving like this, and this motion is called oscillations. So it will go to this point, then it will again rise in this side, then it will come back here, and then it will again rise here, and then it will come back here and rise. And eventually you will notice that the height that this ball rises will start to decrease because of the air resistance, because there are small air molecules, and when we cannot see them, they're almost invisible because they're very small, and the ball is constantly hitting these air molecules and transferring its energy into these molecules. And so essentially at the end, what is left is that these air molecules are vibrating slightly more, and the energy is transferred from this ball to these air molecules, and the ball loses energy. Therefore, it is going to lose some height, and eventually at one point, it's going to come to rest at this position. Now, this position that it comes to rest is known as the mean position of the ball or the pendulum, and the position that I raised it to initially, that height or that position of the bob is known as the extreme positions. So there are two extreme positions, and they're called extremum. One of it will be the same on this side, right? It will look something like this. So these two positions are the extremums, and let me draw this one. This one, when the bob is over here, let me just try to draw it a bit like this. All right, so when it's over here, this green one is known as the mean position. So these extreme and mean are just names, but the concept behind is what I just explained. That's the concept behind these positions. Is that a concept clear to you all? What does it mean for a bob to be in its extreme or mean position? Essentially, extreme positions are those positions that are the maximum height that you raise the ball to, and then you drop it from there or release it from there. That initial position was the extreme position, and the ball is going to come to a rest at some position after some time eventually. That position is known as the mean position of the bob. So is that idea clear?
Yes, sir.
All right. Okay, great. So essentially, that's an oscillation. Now, this is an example of a pendulum. there can be multiple examples. For example, actually, let me just write those. So I'm going to bring this one over here, and I'm going to say that this was the first example of a vibrational motion, and this is the pendulum. You'll have to ignore the spelling. But the second one is simply a vibrational motion, vibrations of molecules. For example, we'll start with a classical example. So you don't have to think very small in terms of molecules, but you can think of something that you're more familiar with. And that's the idea of, let's suppose there are some balls. And what happens is, suppose someone throws these balls on a table, and eventually what's going to happen is all of them are going to collide, hit each other at some point. And when that happens, these balls are have some energies, right? They carry some energy with them, and when they hit each other, there is this transfer of energy happening. That transfer of energy which is happening when they hit each other is vibrations, right? So that's vibrations. You can also think in terms of now, this was an example of some classical balls. We can think in terms of molecules. Now again, I'm going to model these molecules as balls, but they're not really the atoms. They're not really you cannot visualize or assign a picture to them as of some small tiny balls. They're actually really, they're just a wave that is spread across. But if you even go into more detail or depth understanding of these particles, they're essentially just fields. And we talked about fields when we discussed the topic of gravitational fields. And we also talked about fields in the last topic of ideal gases, where we defined a temperature field. And so essentially everything around you is a consequence of the vibrations of a field. And I'll go into that as well. But suppose that you have some molecules. They can be any molecules, atoms that make up something. So I'll try to draw them like this. So suppose it's a surface of any material. And if you look at it closely, you can see atoms sitting like this together. The atoms are never, or you can think of electrons or atoms, they're never stationary. They're always moving. In fact, there goes the saying that the purpose of living or something, it's just that the electron is essentially trying to find a place to rest, to come to a stop, but it never comes to a stop. Electrons are always moving. Everything is dynamical. Nothing is static or boring. So these molecules are vibrating, and this vibrations can also be modeled as an oscillation. In fact, it is an oscillation, and we can we can model this as something that is called a simple harmonic motion. And that's the motion that I'm going to talk about now. Before I go on to that, is there any question from these two examples?
No, sir.
No questions. Okay. So, all right. Now let's talk about the third one, which is something that we'll also completely focus on in this chapter. But it does not mean that we're limited to that particular motion. In fact, it turns out that anything in the universe can be modeled as this simple harmonic motion. And to understand this motion, we use the idea of a spring mass system, or it's also called a simple harmonic oscillator. But before we get into that, how can I define a simple harmonic motion? First of all, obviously, it is going to be a periodic motion, right? And a periodic motion essentially means the same thing as we defined oscillations. It's a back and forth motion that repeats itself, right? Like a like a sine wave or a cosine wave, right? And that's why actually, if you look at a sine or a cos wave, it's a wave or a function that repeats itself. So it's something like this, right? So it keeps on repeating, the pattern keeps on repeating. This is essentially a sine theta function. Anyways, so you can see that this is the repeating function, and we'll see that the equations of simple harmonic motion have this sine or cosine theta in these equations. Now, the other thing for a simple harmonic motion is that the acceleration of any system is proportional to the displacement of that system. In fact, it is proportional to the I'll not say inverse of displacement, but I'll say the negative. You can use the word negative of displacement, right? And I'll tell you why that negative, the significance of that negative sign as well. But let me first write it that any motion where the acceleration of the system is proportional to the negative of the displacement is a simple harmonic motion. If you come back to this example of a pendulum, you can understand the significance of this negative sign, because you see that if I raise this ball or an object to some height and then release it, it always accelerates in order to come to a stop. What that means is it is essentially decelerating, so the acceleration is decreasing, and it is coming towards this center. Hence, it is really decelerating, and therefore the acceleration has, or it carries, this negative signature. So is the idea of the negative sign clear? You can also relate it to the idea of a restoring force, but since we have not talked about forces yet, so I did not mention that as of yet. But still, you can understand the significance of the negative sign from everything that we have discussed, right? So is that clear? The idea of this negative signature in this equation?
Yes.
It's clear. Okay. All right. So from this, we can write down a mathematical equation, and it is not a part of your course to really, see where these equations come from. But I'll just to, make things a bit more clearer to you, I'll briefly tell you where these equations come from in a bit, and then we can move forward. The idea of telling you where these equations come from is the fact that these equations come from something very important in physics. In fact, it turns out that most of the physical phenomena in nature is almost the same, right? It turns out that if nature likes an idea, it uses it over and over and over again, right? So I'll tell you what I mean by that. But before I do so, let me talk about something. Being in A2 level physics right now, I'm sure you're all familiar with the idea of momentum. Is anyone not familiar with what is momentum? I'm sure you have studied momentum in your AS physics. Have you?
Yes.
You're familiar with the idea of momentum then, right?
Yeah.
All right. So you know that momentum is actually defined by really one way or another. It is defined by Newton's second law of motion, right? And you can mathematically write down Newton's second law of motion as, okay, first I'm going to give this thing a heading, but completely ignore what I'm going to write right now. But we'll get into that in a bit. Okay, so if this word scares you or anything, just completely ignore this heading. So I'm just going to get rid of it like that and come to this Newton's second law. We know that Newton's second law mathematically can be written as the force is really the time rate of change of momentum, right? You can write it as, just using the idea of momentum at some point 2 minus momentum at some point 1 divided by the time at that point 2 minus the time at that momentum point 1. And that's that's Newton's second law. Roughly speaking, you can say that this is the Newton's second law. And from here, we come to this equation, which is F equals ma, simply because noting that momentum is mass times the velocity of an object. And if I put these things in this expression, then I can see that force is just, because mass is a constant, it's not, or at least for our purposes, mass does not change with time. So we can remove this mass outside, and now we're left with dv by dt. We know that time rate of change of velocity, how velocity changes with time, is just acceleration, and therefore we get this expression F equals ma. So that's what happened in coming to this expression. Now, what my goal here is to tell you that all of this thing that we have been doing, this is a differential equation, really. F equals ma is a differential equation. It is also known as the equation of motion for a system. You can say that the force, sum of all the forces, is the time rate of change of momentum. But we like to work in a quantity which can be displacement. Why? Because you want to see how displacement changes with time. That's essentially what we want to understand when we talk about equation of motion. So we want to write this expression in dx by dt. And dx by dt, we can represent this thing as some x and a dot on top of it. Now, what does that mean? That means that I'm taking a time derivative of x. This dot on top means I'm taking a time derivative of displacement. Is everybody following along? Or are you lost? Did I scare you too much, or is everybody following along?
I don't get this last part.
Okay, this thing, do you understand? Okay, actually, this was sum of forces. Do you understand this equation though?
Yes.
Okay, so this thing I was just saying over here, that this d over dt, let me use a different color. So I'll d, actually that made it too big. Let me just get rid. Okay, so this thing in blue, d over dt, is an operator, a derivative operator, a time derivative operator, and it's acting on x. Now, I can write the same thing as x and a dot on top of it, which this means that I'm just writing time derivative of x, dx over dt. This thing just means it is dx over dt. Just a notation that we use to simplify our writing. If you're confused with that, don't bother. I'll use the entire thing dx over dt. But do you agree with this thing that velocity is dx by dt? Is everybody agreeing with this thing?
Yes.
Okay, all right. So if you agree with that, then if I write d, suppose I write d squared x by dt squared, what would this be? What I'm doing is I'm just taking the derivative now of velocity, right? But we know velocity is what? It is dx over dt. So I have d over dt, but velocity, this v, is again dx over dt, which means this thing is just this thing, d squared x over dt squared. Before I go any further, actually, I would also like to know, in mathematics, have you studied the topic of differential equations? Are you familiar with differential equations? Do you study that in mathematics of AS or A2 level mathematics?
I'm not
Because
taking mathematics.
uh, no, what I mean is, you're not taking mathematics. That's what you're saying?
Yeah.
Oh, all right, okay. Yeah, I remember even when I was doing A level, my A levels. Uh, Maybe you're from medical. You want to go into medical background, right? Maybe
Yeah.
or yeah. Okay, so I forgot. I completely forgot that, and I was assuming that you would have some of the tools from mathematics. But anyways, is this idea of derivatives clear? I think then you'd have some trouble also understanding derivatives. Derivatives are nothing to be scared about. It is just this thing that you see that the momentum at some point would have a value, and at some other point it will also have a value. If you look at this equation, that means that there are two values of momentum, and the difference between these two values would be P2 minus P1. Now, corresponding to that P2, there will be some time T2. That object might have had that momentum P2 at some time interval T2 and P1 at some time interval T1. So this thing, the difference between these two quantities, considering the time, is now D essentially stands for difference in momentum now, and dt stands for difference in time. You can think of it like that, right? So that's derivative. That's just something that we call a derivative. For now, I think this much is enough in terms of derivatives. So if I say that v is dx by dt, how does my x changes as time changes? That's velocity. And then dv by dt would be d by dt of dx by dt. So that means that d by dt is squared, right? So d squared by dt squared. The operator is squared now. And that we know is acceleration, right? Change in velocity as time changes is acceleration. So which essentially just means that I can write, if there are two derivatives of x, so I'll not get into that dot expression, but I can write this equation as x d squared x by dt squared, which is acceleration, times mass is equal to sum of all the forces. So my goal was here to tell you that even Newton's second law, which is ma, but a is d squared x by dt squared, is a differential equation. And exactly in the same way, we have a differential equation that models this oscillatory motion, waves and oscillations. So I wrote an expression before that was A is directly proportional to minus the displacement. And the mathematical expression, if I write it as A is equal to the constant of proportionality, turns out to be something that is omega squared. And then I have X, right? Now this omega squared is the constant of proportionality, that constant K, right? But you must be familiar with omega. Omega is just the angular frequency of an object, right? Something that is oscillating or moving in a circle, it will have a frequency, and that frequency is angular frequency. We have talked about it in circular motion. If you're in one way or another not familiar with that, you can let me know, and we can quickly revise that. But if it's okay, you understand what angular frequency is, then we can, or it's also known as angular velocity, omega. So it's actually known as angular velocity. So if you're familiar with that, I can move forward. Do you understand what this omega is? If something is, for example, moving in a circle, it will have two types of velocities. One is a velocity that is completely translational, that was v, and the other is the velocity of its rotational speed. That's omega. That's the angular velocity, right? So my goal was here to tell you that this equation for acceleration that I have directly written down without going into its mathematics, and you don't need to go into its mathematics, this equation actually comes from a differential equation like this, right? But you don't have to know at this point in your studies that where does this differential equation come from. These are linear differential equations, and in the study of physics, what we do is we use these differential equations to understand almost everything that we understand or write an equation for in physics essentially comes from a differential equation, right? So differential equations are very important, but you do not go into their depth in your A levels or A physics. In your university level, you'll of course understand these things better, but that's this thing. Now we can come back to a simple harmonic motion. We have almost 1 minute remaining. So I think I'll end with by relating this simple harmonic motion to force. This is the equation for acceleration of a simple harmonic motion. Now I can immediately relate this to force, where force is, we know it's ma, right? But acceleration is what? Multiplied by, acceleration is minus omega squared x, so minus omega squared x, and this equation becomes force is minus m omega squared x. So this is that force. It's known as the restoring force, right? This force is known as the restoring force. And if I go back in this pendulum example,